190 Southwest 901. Level 320, Delta 471.
Afternoon, Boston American 1643 added 0, and then to 11,000 at C-Dog.
So you can see how the detector,
30016.
once the noise goes away, the voltage drops. That allows the tube to release its grip on the first audio stage, and the audio opens up on the first audio stage. As long as we have this positive voltage that's caused by noise, the shunt tube will be dropping that plate voltage on the audio amplifier close to zero.
We're about 303 knots. What do you need? 12622. Thanks very much. Have a good night. Southwest 4404.
So, as you can tell, there's been a little delay getting this last video out on the super-regenerative receiver. And being that summer has hit, I've been out fishing and doing other things. It's pretty typical for my video production to slow down during the summer. But I can't use those excuses completely. I really ran into a problem with trying to build the Squelch circuit for the Super-Regen. It turned out to be actually harder than getting the Super-Regen itself operating. Adding this third tube, which is a double tube, to do the squelch function turned out to be a very tough nut to crack, and much more work than I thought it would be. Remember, what we're trying to do is eliminate that raucous noise, rushing noise that comes out of the Super-Regen, and only open the squelch so we have audio coming out when we have a nice strong signal. I've added the Squelch Control back here near the squelch tube. I'm running out of room on this chassis. Luckily I was able to fit the circuit inside. So the control tube itself is the very popular 6U8, 6EA8, 6GH8 style triode sharp cutoff pentode. And we're using the sharp cutoff pentode as the muting switch. So I hope you enjoyed this video. We're going to go through some tube substitutions in the regen part. Remember, I talked about using the 12AU7 possibly, and maybe the 12AT7 in the RF spot, and we'll go through that as well. So this is the final chapter on the Super-Regen VHF receiver. So adding a squelch to the Super-Regen has always been an interesting thing that I've considered, because if you ever owned a Heathkit 2er, 6er, or 10er, or the CB version, you'll know that that constant hissing can really get to you after a while, and you really would like to have some kind of squelch. With all of that noise, and knowing that the noise generally goes down with a stronger signal, probably a squelch circuit could work. So normally a squelch circuit is not using noise as the trigger to turn off the sound to the speaker. It's using the automatic gain control or the detected carrier to switch the squelch. But in this case, we're going to try to use the noise of the Super-Regen and filter that noise at a certain frequency that is out of the audio passband, and we'll come up with a squelch circuit. The third thing that I'd like to handle with this is the conversion of the 6BZ7 and the triode pentode in the original circuit to a 12AT7 and a 12AU7. Now I understand that the 12AU7 is not going to have as much power output as this pentode that's a video amplifier and TV, but it should be able to put out enough noise that we can drive a speaker with the 12AU7. So these two 12-volt tubes will replace the two 6-volt tubes. So the next step is to try to convert the super-regenerative receiver to be able to utilize the 12AT7 and the 12AU7. And I've got the European versions listed on the schematic. The ECC81/CV4024, which is the equivalent of the 12AT7, and the ECC82/CV4003 is the 12AU7 Euro equivalent. Now it turns out that pin 9 on the original tube, the 6BZ7, 6BQ7, was an internal shield that I grounded. That turns out to be the center tap of the filament on the 12AT7, so that works out very nicely. And the 12AT7 will simply plug right in and light up. We do have to do one swap. We have to tie pin 5 and 4 together. So instead of pin 5 being grounded, it gets connected to pin 4, because those are the outside of the filament. So it's not going to just work when you plug it in, like I said. You do have to do that one change. You have to tie 4 to 5, and then 9 is grounded, and it should light up nicely when you put 6.3 on 4 and 5. Now, unfortunately, V2 was wired for a triode pentode, and to make that work with a dual triode, we need to remove a couple parts, and we need to rewire all of the pins. Basically, they're pretty much all wrong, so that's got to be rewired for the 12AU7. And we'll see if one section of a 12AU7 can drive a speaker. I think it will at a low power output, but it should be okay for room volume. If this does not work out, then we'll have to go to a little larger tube like a 12BH7, which is a higher plate dissipation dual triode. But we will attempt to do this with the 12AU7. Okay, some rewiring has been done. I now have a 12AT7 in the detector section and a 12AU7 in the output audio amplifier section. So this was a fairly extensive rewire on the 12AU7 because the pinout is completely different. However, the pinout on the 12AT7 is very similar to that of the 12BZ7. Just had to handle the filament a little different because it's wired a little bit differently. But I can say now that it does work. The audio output is a bit lower. You can tell that the 12AU7 is not very effective as a triode Class A speaker amplifier. It would really like to have higher voltage, like maybe 180 or 200 volts, but this shows it does work. I think you'd like to be running it up around 150 to 180 volts to get back to some high performance like we got with the other setup. So I tried another 12AT7. This one goes in just about like the 6BZ7 at 100 volts. I'm going to say that the 12AT7 is going to work just as well as the 6BZ7 for the RF. I also substituted in several of the 12AU7 types, and I even put in a 12AX7. Which was notably lower in output. So the AU7 is definitely capable of a little more power for the speaker, that's for sure. If we increase the voltage to 150 volts, or something close to it, you notice the volume comes up a little bit, and it goes into regeneration at a lower point. So I just wanted to show you that the circuit is very tolerant of voltages between 100 volts and 150 volts. 200 volts shouldn't be a problem for this. Might even work better. Just stuck a 12AU7 in place of the 12AT7, and with the regeneration control not moved. So let's see if we can get it to work. No soap radio, as they say. 12AU7 will not work in a VHF circuit. It just has too much capacitance, and you'd have to do some real playing to try to get it to work. Perhaps you could do it with external quench, but I think the problem is it just has too much capacitance, and we don't have a Colpitts oscillator that's working properly.
Say that one more time for 922 Tango.
Now I have replaced the 12AU7 with the 12BH7.
Say that one more time, I'm sorry.
And now we're starting to get some audio out. Of course, the 12BH7 has much higher power triodes.
Hotel Oscar Charlie Kilo Echo Hockey 922 Tango.
And it certainly is acting more like the 6AW8. So here's a dual triode that's doing a pretty good job in the final. Same wiring as the 12AU7, I just simply plugged it in.
28.2 American, 2681.
Now something I did notice was that by using the 12AT7, that the frequency on my dial shifted down a little bit, meaning the 12AT7 definitely has a little more capacitance than those fancy TV dual triodes. And you would have to spread the main coil out a little bit to compensate, to make the dial work again. So not as big a difference as we saw between the pentode and the triode, but certainly the 12AT7 has a little bit more capacitance than the 6BZ7. So what I've got here is a lead attached to the plate of the voltage amplifier, right here, the plate. And on that plate we would expect to be somewhere on the load line. And it looks like we're at about 31 volts. Now that tube is only handling very, very low level signals, so 30 volts is a fine place to be. We're not going to be swinging more than a volt, so that's okay. So this lead is being fed by a 270K resistor. Now what would happen if we suddenly introduced a low impedance on pin 1 and took that plate down closer to ground so that we starve the voltage to the tube? I'm going to do that with a resistor. I've got a 1K resistor, and I'm just going to put that right across and see if we can't short that baby out. Oh my! Half a volt. And did you notice that the audio went away? If I don't shock myself here. Okay, so what I've just done is found a place where with just a simple 1K resistor I can mute the receiver. So that's going to be my plan for my squelch circuit. Rather than listening to this noise all the time, we will have a way to sense the noise and have a squelch control on the receiver. And that's how we're going to kill the audio, and turning the tube completely off. So going into my library of classic ham magazines, I found this issue of 73 magazine, August 1963, and I'm going to turn you on to a website which gives you all of these in PDF form, and it's a very big library of interesting projects. 73 was always loaded with lots of projects compared to the other magazines. So here's the article, A Squelch for the Tour and Sixer. So, you know, the guy starts here, Richard Koenig, he says, the amazing little Benton Harbor lunch bucket is a very popular transceiver and is found in practically every ham shack for the communications of one type or another. Although their performance is excellent, the characteristic hiss noise from the Super-Regen receiver can be somewhat annoying while monitoring for any length of time, and I will attest to that. So he came up with a kind of a squelch circuit that has to work, and to say it's a bit primitive is an understatement. As you can see, he's taking the audio right off the primary of the output transformer to the speaker, sending that back through a kind of a high-pass filter that he's made with this choke and low-value capacitor, rectifying it with this bridge, and then on one side of the bridge he has a voltage divider off B+, and the other side of the bridge he's got going to the grid of a control tube, a 6AV6. The 6AV6, when the squelch is set at critical point, will switch and turn on this relay, which opens the contacts to the speaker, thus squelching the circuit. Now that's a pretty simple squelch circuit, and it's all being done in the 6AQ5 output amplifier, the speaker amplifier. Very clever way of squelching the tour. That's a little bit too crude for what I think we can accomplish using a one-tube type circuit. So let's see what we can come up with to squelch the Super-Regen. That won't involve having to use some kind of a relay. Okay, let's look at the squelch circuit a little closer. I think we need to start with a foundational squelch circuit, and you can't get much simpler than this one, guys. This is the old-fashioned relay squelch, famously used on the Collins R390 straight, and this is a very popular first principle squelch that just uses the automatic gain control or automatic volume control, negative going voltage with stronger signals to turn a tube on and off. So if we start out with the AGC at 0, typically the tube is biased so that it is on. The relay is drawing the lever down, and that would cut off the audio. In the other case, the AGC begins to become more negative with a stronger signal, and that turns the tube off, the relay releases, and now you have this condition. Either condition can be used in a squelch circuit with the audio. If we use these two contacts, we can do parallel or shunt type muting, that is, shorting out the audio. And if we use these contacts, opening and closing these in series with the audio similarly can kill the audio. In the shunt case, we can replace that mechanical relay with a tube type relay. Tubes can be made to work as switches, DC switches, and the automatic volume control, the negative AGC, whatever, can be used to turn this audio stage on and off, which literally shorts the voltage out on your first audio stage. So this is a very clever shunt type audio relay system. Now, once that the age of the two-way radio, the mobile two-way radio hit, and you had FM and AM type radios and CBs, the squelch circuit became more organized and it became more standardized. And most of them used a system that cut off the audio tube in the grid circuit rather than just shorting out the plate. So this AGC system on this particular CB, the Johnson Messenger, it literally upsets the bias on the first audio amp, turning it off, and now the audio is interrupted. And these Citizens radio telephones, or CB radios, when they first came out, it was a big deal. Now everybody could have a radio in their car and their boat and so on. This is just another AGC-based squelch system with a relay. Now that shunt case, you could replace that shunt tube with an enhancement mode MOSFET. The IRF 840 is just an example of an enhancement mode MOSFET that could be used to short out the plate voltage on the first audio stage. This is a Motorola circuit using those 12-volt space charge tubes. And this is a little different. It's not using the AGC. It's using the noise from the discriminator. And that noise from the discriminator is separately amplified. First it's high-pass filtered, separately amplified, rectified and turned into a DC voltage that cuts off the tube. In this case it's a pentagrid tube. And the audio is blocked. So this is one of the first noise-type squelches. But most of the CBs, like this Sonar model FS23, they do use the grid bias circuit. Let's take a little closer look. The Sonar 23 is a classic CB radio. The AGC is used to control a squelch amplifier tube. The squelch amplifier tube disturbs the audio in the grid circuit of the speech amp. Actually, not in the speech amp. In the speech amp doubles as the first audio stage for the speaker amp as well. So it's doing double duty, as most circuits that can in CBs do. What else we got here? This is just another grid bias cutoff type. This could be used with AGC, or as they say here, noise from a rectified noise. This could be used as a noise squelch. So it's a very flexible circuit. So I was armed with all of this information when I decided that I had to put a squelch on our super-regenerative bomb. This little radio will quickly drive you crazy if you listen to the rushing noise from the speaker too long, waiting for an aircraft signal to show up. The duty cycle on those aircraft transmissions is so low, you generally will go nuts before you actually hear something. Usually the aircraft are busy at a specific time of day, and that's when you can hear a lot of traffic. So I took audio right off the top of the audio volume control, right here, and I sent that up through 2 stages of high-pass filtering. So that's 40 dB per decade of high-pass filtering. Now I wanted to set this up so that it cut in somewhere around 5, 6, 7 kilohertz above the area that we're listening to for audio speech, because I figured the noise above that is what I want to use to control my switch. This is being amplified by the first stage of the 12AU7, and then there's a positive voltage detector. The positive voltage detector turns it into a positive DC, and the positive DC is used to control the squelch tube, the second section. Now, to use a tube as a switch, you have to be able to set it at the critical point between 0 and the positive place where it actually turns on. So you really want the tube to be a little bit negative to make sure it's completely off before you turn it on. In order to simulate this without having a separate negative bias supply, which I did not want to do, by the way, I did not want to have another power supply down here that was negative 100 volts or something, or negative 20 volts. So the way that we synthesize that negative voltage is by bringing the cathode slightly above ground with this potentiometer. Now with the cathode slightly positive, this slightly positive makes the grid look negative, and now the positive voltage overcomes the negative, the tube finally turns on. And when that tube turns on, it shorts out R12, and with only a couple volts left on the plate, the audio goes away. So that's the theory. Now, I did have some problems with the 12AU7 as a switch. It was too soft. And by soft, I mean I did not get clean switching with the tube.
By the time the noise was rectified and turned into a positive voltage, and that positive voltage turned the tube on, when the noise went away and speech came through, it didn't release enough to turn the tube back off again and allow the audio to come through. So I had a real problem with the 12AU7. I couldn't get it to work in this circuit. Another issue was with only 270K, I wanted to have a little more chance of cutting the tube off, so I went up to a 470K. I fooled around a little bit with the filter as well, and finally I moved the volume control over here, and I found that there was an effect where changing the volume was starting to affect this filter a little bit. I was getting some interaction that I did not like. So I did move the volume control over here. Also, I went back to a 6AW8. The 6AW8 uses a pentode in the power amp stage, and it gave a lot more power gain. I liked it better than using the dual triodes, even the larger dual triodes. So where do we end up? So where I ended up was something that looks pretty much the same. It's not radically different. But I'm now using the 6U8, the classic triode sharp cutoff pentode. This gives a little more sensitivity, and it has much sharper switching characteristics. It's much more sensitive. I got rid of the pot on the cathode and replaced it with a stiff regulated 1.4 volts set up with these two diodes. And now the Squelch Control becomes the gain of the pentode. And this worked a lot better. Eliminated the resistor. It's fine. These two tubes can certainly handle anything that we can throw at them. 150 volts on both plates. There's no need for a series limiting, current limiting resistor. It just shorts it out very nicely. Now you can see the audio pot is on the power amp. That worked very well. I have a fixed bias here and a fixed bias here. So I've improved the circuit a little bit, but it generally is the same circuit, just dressed out a little more.
Checker 42340. Canada 857. Yeah, I'd like to go down to 340, getting a little light chop here, 36.
So we now have a squelch on the Super-Regen.
42320.
And let me tell you, the Super-Regen will drive you nuts with its rushing noise in short order. So building a squelch circuit for it, while it turned out to be much more difficult than I anticipated, and probably 2 or 3 times harder than getting the Super-Regen part itself working, it really is a nice thing to have on this radio. Now, of course, we've got 3 tubes now, and all of them are double tubes, and you're thinking, wow, I could almost build a full super het with that many tubes.
Change flight level 340, Canada 857. Thank you.
But with the Super-Regen, I think we've got a winner here. It took a little longer to get this tamed, and truthfully, I had a lot of work going on and travel, so that's why this video is a couple weeks late. But it is done. So I've picked up a new control, the Squelch Control back here. I didn't have any room for it, so I put it back by the Squelch tube. This is the Squelch tube. And I've got 3 candidate tubes that I've been working with. The 6U8, of course, the 6GH8, and I've got a 6EA8 in there working right now. Now, when you pull the squelch tube out, the unit will become unsquelched, so let's do that. So this is what you would be hearing if there was no squelch, and that can get to you. So we came a long way in developing a working schematic. Truthfully, this is so many stages that you could probably start to talk about doing a full-blown super heterodyne receiver for VHF. But this is still a lot of bang for the buck. I have enjoyed doing the series, and I hope that this lasts a while. There's no doubt in my mind that solid-state super-regen receivers are much easier to work with. This was kind of a labor of love to do it all tube style like the 1940s and 50s. But a lot of this is not properly published, especially the noise squelch section. So having a decent circuit, one that can be innovated upon and published on the internet, is going to help people for other types of radios that need a squelch. A noise squelch is very practical for receivers that do not have a very good AGC, or automatic volume control. So see you next video. Hopefully we're on to something a little more interesting than the Super-Regen. So just a little epilogue to this video about adding a squelch to the super-regenerative receiver. Some years ago, in the late 90s, I worked at Analog Devices, ADI, as an applications engineer. And I actually worked with Chuck Kitchen, N1TEV. Charles, or Chuck, he used to hold these extravagant parties at his house. And sometimes we would have little circuit contests. And at that time we were building solid-state super-regens like this one. This one covers the aircraft band, and it has a common base amplifier and an FET running as a super-regen stage. And then it would typically go to an LM386 over here, and that would be your receiver. So he challenged me to make a squelch for a super-regen. And this is what I brought to that party back in 1998. It was a Christmas party, and basically it showed a squelch working with a super-regen. Now, unfortunately, it took a complete quad op-amp to pull this off, and he laughed at it and said, "That's ridiculous. That is way too complicated. Nobody's ever going to build that thing." And this went into the junk box, never to be seen again. But knowing Chuck, he immediately started working on his own circuit based on what I had done and his own experiments. He came up with a far simpler solution. And here's the schematic of that solution. As you can see, he's cleverly using another LM386 as a noise amplifier, and basically an FET as a series switch, cutting off the FET and killing the audio. So that's what came out of a party back in the 90s, a squelch for a super-regen.